mathematical numbers. So we start with counting numbers. So when we have a basket of apples, we would start with 1, 2, 3, 4, 5, so on and so forth. So those are called counting numbers. And the fundamental theorem of arithmetic says every counting number greater than 1 is either a prime or a composite number. So what is a prime? A prime number only has 1 and itself as factors. Let's see these numbers. So 2, 3, 5, 7, so on and so forth. They only have 2 factors, 1 and itself. 2 is the only even prime, and it's the smallest prime. Notice 1 is not a prime because 1 only has 1 factor. So what is a factor? A factor is also a counting number. Let's give an example. So let's see 12, number 12. 12 can be written as 1 times 12, or 2 times 6, or 3 times 4. So we call 1, 2, 3, 4, 6, 12. We call them factors of 12. So they are factors of 12. And 1, 2, 3, 4, 6 are called proper factors. So not including the number 12 itself. So called proper factors. But some books or some people may also think, 1 is not a proper factor either. But for us, usually, I consider 1 as a proper factor for any number. So a prime number can be thought as, or only has 1 as a factor, as a proper factor. Right? Only has a prime, only has 1 as a proper factor. Right? Because any prime number has 2 factors, 1 and itself. Something called a parametrization. Parametrization is written a number in the product of primes. You see this case 12 can be written as 2 times 6, but 6 is not a prime. 2 is a prime. So 6 can be written as 2 times 3. So now we see 2 times 2 times 3. So it's all prime. So this is called a prime factor. So 2 times 2 times 3 is a prime factorization for 12. Or parametrization for 12. A composite number. Composite number versus prime number. 2 has more than 2 factors. Right? So it can be written as a product of its proper factors or its factors. Let's see 4, 6, so on. All the even numbers except 2 are composite numbers. So 4 is the smallest composite number. So 4 can be written as 1 times 4, 2 times 2. So 4 has 3 factors, 1, 2, and 4. And 4 has 2 proper factors, 1 and 2. So after counting numbers, the next one is a whole number. So whole number only has 1 number different from counting numbers. So whole number including 0. So the difference between whole number and counting number is only 1 number, 0. Abundant number. Abundant number means the sum of its proper factors is greater than the number itself. 12, 18, 20. So I have a list of up to 100. Those are abundant numbers. Let's use 12 as an example. So 12 has proper factors of 1, 2, 3, 4, 6. So add this up, 6, 16, which is greater than 12. So that's why 12 is also called abundant number. Perfect numbers. Perfect numbers means the sum of its proper factors is equal to the number itself. So within 100, there's only 2, 6 and 28. Then the next one is a 496, 8,128. And a couple of years ago, we find this one. Okay. So perfect numbers are not as many. Let's say 6. 6 is the smallest perfect number. So the factors of 6, proper factors of 6 is 1, 2, 3. So add those 3 up, that's a 6. So that's a perfect number. Deficient numbers versus abundant numbers. So sum of its proper factors is less than the number itself. Right, let's see 1. Right, 1 has no proper factors. So its sum is 0. So 0 is less than 1. Then perfect squares. Perfect squares means a number can be written as another number square. 1 is 1 square, 4 is 2 square, 9 is 3 square, so on and so forth. Palindromic numbers. Palindromic numbers, all the digits is 0 up to 9. Then 11, 22, 33, up to 99. This is within 100. Then in the 100 range, 100 range, we'll have 101, 111, so on and so forth. Then 200 range, I have a list. 300 range, 400 range, then thousands, right? You see that's a middle number. That's a middle number. Then on the left-hand side and right-hand side of the middle number, there's a symmetry. There's a symmetry. You see there's 1, 0, 0, 1. 0 in the middle. Maybe I should add a 0 here. And of course, 1, 1, 1, 1, so on and so forth. Right? And a special palindromic number is called Damello numbers. Damello numbers. So it's a special type, which is 1 square equals 1. So smallest one is 1. And the 121, which is 11 square. 1, 2, 3, 2, 1 is 111 square, and so on and so forth. So we see the pattern here. If it's only 1, so that's a 1. And if it's 2 1s, which is 11, we see 2 in the middle, 1, 2, 1. 3 digits, 1, 1, 1, we see 3 in the middle, 1, 2, 3, 2, 1. 4 digits, we see 4 in the middle. So to know this pattern is good for us to sometimes simplify or to factor or to simplify. So this is just one example, multiplying 4 1s square, 1, 1, 1, 1 square. And we get 4 in the middle. So the 1, 3, 1, 2, 3, 4, then 3, 2, 1. So integers. Integers are whole numbers plus negative counting numbers. So whole numbers from 0, 1, 2, 3, counting to the right, getting bigger and bigger until infinity. Infinity is another number. It's not idea, it's a concept, which means just, the numbers are getting bigger, bigger, and bigger. On the left-hand side of 0, that's a negative counting numbers. Negative 1, negative 2, negative 3, so on and so forth, until negative infinity. Negative infinity is also non-concept. It's not a number itself. It just means the number becomes smaller, smaller, and smaller. This line we call real number line. So 0 sits in the middle, and we call 0 the origin. The origin. Then on the right-hand side of 0, positive numbers. So to the right is positive direction. To the left of 0 is a negative direction. So negative numbers. So numbers get smaller and smaller. Fractions or rational numbers. So a fraction is a number that can be expressed as a ratio of integers. So a numerator, which is an integer, a denominator, which is also an integer, like this one, half, 1/2. So we're treating this triangle as one thing, right? So this is green, the green part is a half of this triangle. 2/3, we have a disk, right? Then the purple part is 2/3 of this disk, treating this disk as one thing. We're treating this rectangle as one thing, then the shaded orange color is a 4/5. So the fractions. Irrational numbers. A number cannot be expressed as a ratio of integers, which means a number there's no way we can write as one integer divided by another integer, like a pi, famous pi. Right? Pi is a ratio between the circumference of a circle and its diameter. So sometimes we use a 3.14 to approximate pi. But a pi is an irrational number. It's just, if you're calculating, it just keeps going. That's a computer have been calculating pi for over 30, 40 years now, and it's still calculating the next digits every day. The famous Euler number. Euler number is we use E to represent, equals to 2.71. A to A keeps going on. So this is an interesting graph, 2.71, A to A, keeps going. The golden ratio, right? It's like a perfect proportion of things. We use the phi, Greek letter phi, to represent. Is 1 plus square root of 5 over 2. So square root of 5 is called a radical number. Radical numbers, like a radical 2, radical 3, or square root of 2, square root of 3, square root of 5. So square root of any prime is a irrational number. Right? So how do we picture those numbers? Let's see square root 2. We can form a triangle, right? Form a triangle, the two legs, a right triangle, the two legs are 1. So our 1, by Pythagorean theorem, says the sum of two legs squared equals the hypotenuse squared. So in this case, we can somehow visualize square root of 2. Right? So all above numbers are called real numbers. Real numbers means if you square the number, it cannot be negative. If you square a number, it's not negative. It's at least 0 or positive number. So versus imaginary number. So in imaginary numbers, imaginary number defined as I, this I equals the square root of -1, which means I squared equals to 1. I cubed equals to -I. I to the 4th power is 1. And then with real number and the imaginary number, we can form complex numbers. So a complex number has a real part, has imaginary part. A plus BI or A plus IB. I indicates imaginary part. Right? So that's all about the basic numbers we use in basic mathematics.